So here we got the formula for delta S, which is Q over T, which is the same as delta H over T, okay, because Q equals delta H. So let me show you how to use this. So we have mercury, and it is silvery liquid at room temperature, and it normally freezes at negative 38.9 degrees Celsius. So it's a liquid right now, and you have to get it colder to make it freeze, okay, at negative 38.9 degrees Celsius. Molar enthalpy of fusion. So fusion is the energy or the heat, in this case, the heat you need to melt it. So fusion means melt. So I drew a picture right here. You have solid mercury. You are melting it. If you melt it into a liquid, you have to put in endothermic. You have to put energy in to make it melt. That's what that means. What is the entropy change of the system? When you have this much mercury, okay, so delta S is what they're looking for. So I wrote the formula, delta S equals Q over T, okay? But when I'm plugging in the numbers, okay, first, this is delta H. So I'm wondering, should I use that? Well, that's not Q. Well, delta H is the same as Q because there's no work. Remember the formula up here? That Q, heat plus work, is equal to the delta H. So there's no work, so heat is the same as delta H. So I'm just going to plug that in, 2.29 kilojoules per mole. Okay? But I am freezing it. So going to the right, I'm melting it. So going to the left, I'm freezing it, which means I must take this energy out. So that needs to be negative. Okay? So it's exothermic. I have to take energy out of the liquid to make it freeze. Okay? And this happens at negative 38.9 degrees Celsius. And I change that to Kelvin down here. It's 234 Kelvin. And that's it. You just divide the numbers. But you have to make sure that you change this to, this has to be in joules. So I went ahead and calculated, I have 50 grams of mercury here. I changed that to moles, so I got 0.249 moles. And the reason I did that is so that the moles will cancel here and here. Also, I'm going to change this to joules. So it'll be 1 kJ is 1,000 joules. Okay, dividing those numbers, the kJ will cancel here, and you're going to end up with joules divided by this, and you're going to get a number that is negative 2.43 joules over K. Okay, now what does this number mean? This is the change in entropy. So it's negative, meaning that's bad, because it became more ordered. Okay, so remember, you have entropy here, the S. It goes from solid at 0 entropy, liquid has higher entropy because there's more random, and gas is more random. Okay, so if it's going from, let's say this is solid, this is liquid, right? So it's going down in entropy, that means it's negative. Okay, that means it's becoming more ordered, going backwards this way. Okay, and what that means is this is the amount of heat that flows at this temperature, and that's what entropy is, okay, quantitatively. So the second law of thermodynamics states that the entropy of the universe increases for spontaneous process. So for every spontaneous process that happens right now on Earth, our universe's delta S is changing, and it's always increasing. Okay, so let me show you what I mean by that. So if the delta S of the universe is 0, that means you have a reversible process. You can go back and forth. You're not really changing anything. But if it's irreversible, okay, that means something spontaneous just happened. You opened a bottle of perfume and it expanded into a gas. Okay, that's irreversible unless you put work into it, right? So it's irreversible. It's spontaneous. If that happens, the delta S of the universe is going to be greater than 0. It's positive delta S. Okay, it means that the entropy of our universe is increasing because of all the spontaneous things that's happening, expansion of whatever. And let me show you an example. What happens to the entropy of the universe when you melt ice? Do you really think it's affecting the randomness of the universe? Well, let's see. I have my hand here, and I'm holding some ice. Okay, so my hand is the system. Okay, I'm sorry, my hand is the surroundings, and the ice is the system, is what we're studying. Okay, so the system is the ice. So 6.01 kilojoules per mole is the amount of energy you need to melt ice. And let's say we have 1 mole of it, and I'm going to change kilojoules to joules. 1,000 joules is 1 kJ. So this is, and this is happening at 273 K. Let's see, it's melting. So this is the system. So this is ice, your ice is melting. So that happens at 0 degrees Celsius, right? Okay, that's when ice melts. So if you do this math, you go this times this divided by this, you're going to get 22.0 J over K. That's the delta S of the ice. It's melting, it's positive because it's becoming more chaotic. It's turning into liquid. Now let's look at the surroundings. So the same energy that went into the ice left my hand. So the energy went from the surroundings to the ice. So it's negative 6.01. Let's say I have a mole of my hand, of the molecules in my hand. The same thing, 1,000 joules per 1 kilojoule. And my hand is warm. It's at 310 degrees Celsius. So that's about 37 degrees Celsius because my body is about 38.6, right? So my hand is warm. You do that math, I'm going to get negative 19.0. Okay, so what I'm doing is I'm going to add the delta S of the system, which is 22.0 J over K. Add that to the delta S of the surroundings, negative 19.0 J over K. When I combine the system and the surroundings, I'm going to get the entropy of the universe, and I'm going to get a positive entropy, 2.6 J over K. So what that means is, yeah, when I'm melting ice, the entropy of the universe is increasing. Okay, and that's just not the only spontaneous process on Earth. There's a lot. Okay, so that is the entropy of the universe, which explains the second law of thermodynamics.